on section 7.1, the central limit theorem for sample means. This one says the length of time in hours it takes for an over 40 group of people to play soccer match is normally distributed with a mean of 2 hours and a standard deviation of 0.5 hours. The sample size of n is equal to 50 is drawn randomly from the population. Find the probability that the sample mean is between 1.8 hours and 2.3 hours. Label and shade the normal distribution and use GeoGebra to find each of the following probabilities. So we begin in this example and we'll complete all that. Let's go first here for the checkoff list. It's to show the following must be true before you can move forward. So the first case here is, do we have a sample size greater or equal to 30? And to verify actually both of these may be true, we just need to check off one box. Okay, coming back here at the top, that first sentence there, it says that the length of time there, the over 40 group to play soccer match is normally distributed. So we're set there. And the second part of that, in that next sentence, we have n is equal to 50. So actually both of these are the case. So I can check off both of these boxes here. So we have a sample size greater than or equal to 30 there at n is equal to 50. And we also know the original distribution there for the length of hours there is also normal. That being the case, we can fill in the following here at the bottom, dealing that for random variable x, particularly that first sentence. It says that we have a normal distribution. But using the other information there to fill out for the mean and standard deviation, we'll do that as well. So let's go back up to that first sentence there, outlining that group. It says the length of time it takes for the over 40 group to play soccer is normally distributed here with a mean of 2 hours and a population standard deviation of 0.5 hours. So that will complete that part before we end up taking the sample for random variable x. So again, for that group, we have the mean is 2 hours and the standard deviation is 0.5 hours. Coming over here next door, we can fill in the information because we've satisfied at least one of those must be true. We've checked off both of those boxes. Now we can go ahead and fill in for x bar. What do we know about the sample size here in this case? That we know that n is equal to 50. There, so there's 50. The mean is the same by the theorem that because we met the requirements, they're both equal to one another, but here for the standard deviation, you want to take it and divide that by the square root of the sample size. And by the way, coming over next door, and this is the reason why that I have a sample size for 1 just for the random variable, because we can always consistently do that. That if I take the standard deviation and divide it by the square root of, in this case, 1, you'll still end up getting the same thing because 1 is a multiplicative identity in that way. 1 times 1 is 1. It's not going to affect anything. 0.5 divided by 1 is still itself. So I want to be real to that fact and do that. And then here we're going to grab a calculator and just round these to, we'll say 4 places for rounding for simplicity reasons. So let's go ahead and grab a calculator and do that. Let's start off here with a 0.5. Then I'm going to divide that by 50. Here I'm just using a simple calculator. So what I'm going to have to do is hit the division button, type in the 50, and then hit the square root. So up there is a square root of 50, then equals to divide. And there's our answer, the 0707. So then 4 places there would be 0.0707, or properly pronounced 707 10,000ths. All right, and that last point down there, we know that because we passed the test there for the 2 check marks, we're always going to be normally distributed for the distribution of sample means. So now that that's set, I can go ahead and fill in the graph down here below, putting the mean in the center. And again, this is a distribution here for x bar. And we want that distribution of x bar because we're going to end up using this information later to estimate the population mean. particularly when we get to chapter 8. So there in the center is 2, and now I want to count those standard deviations. Again, being aware that we're using this new information, that we have a, I guess in a sense, a new mean, even though it's the same, and a new standard deviation. No longer am I using the 0.5 hours. So maybe even for graphing reasons, just to make that a little more simple, we can use that and round that off to, let's say, like 0.07 instead of carrying that to 4 places, maybe even 0.1 hours. So here, to fill it in, we have a huge decrease from going from a half hour to, say 0.1 hours or something like that in that case. Well, actually, it's not probably a big decrease, but it is a decrease nonetheless when you're dividing by square root of n. So the larger the sample size, the smaller the standard error is going to become. And then directly relating that to here, just to make a note that this number is the standard error. So right here, this is called the standard error of the mean. Later, the verbiage there of the mean is going to get dropped off, and then we're going to just start calling these a standard error. And again, the standard error by definition is the standard deviation of our sampling distribution. So we have a new standard deviation. Let me go ahead and add 0.07 in this case. So the next number is going to be 2.07, and again, plus another 0.07, 2.14, and again, third time here, 2.21. Going backwards with subtraction, subtract 0.07, 1.93, pretty simple here. Let's keep going, subtracting another standard deviation, minus 0.07, 1.86, and then finally here at 1.79. So that's completed according to our empirical rule. Now we can go back and answer for the following probability. And what they want here is find the probability that it's between this case, kind of like another example that I did previously before, between 1.8 and 2.3 hours. And then just to iterate here, that both of those are averages. This is an average for a group of 50, for 50 players, not for an individual. So coming up here, let's go ahead and locate both of those numbers here. For the lower, they want, let me do that in a different color here, 1.8, so just right there. Maybe I'll squeeze it maybe right between, maybe do this a little bit better here. That's still not to scale. Yeah, it just kind of bothers me a little bit. Let me do that one more time. Okay, so 1.8, just a little bit above there at the 1.79. So here on the lower end, we've got 1.8, maybe even call it 1.80. On top there, we want the 2.3, maybe even look at that 2.30, and you'll notice that that's way over here at the end, 2.3. Let's make it 2.30. So virtually you can see that I'm shading everything under the curve, and this is just to trick you because a lot of people end up using the wrong standard deviation. They still want to focus on using the 0.5 in this case, but with a smaller standard deviation, I end up shading everything, so the answer naturally should be 100%. But let's go check that out for sure. Let's jump back over to our calculator and plug those values into the normal calculator. In this case here, I want to choose, again, the normal calculator with a mean and standard deviation. So here the mean is 2, and the standard deviation again is our 4 decimal places there, 0.0707. Here we want the 2 facing brackets there. So for our lower bound, we'll grab, again, that number 1.8 for the lower, and the upper was the 2.3. Done. Click the bottom right box there, 0.9977 or 99.77%. That's almost right there, just at 100%. So perfect. I almost have everything shaded. That should make sense there. And again, for our shaded area, the answer is 0.9977 or you could look at that as 99.77%. And there's your answers there, answering for the probability for this question. Find the probability that an average between those 2 hours there for a group of these 50 over 40 soccer players. So this completes it here for this example in this section 7.1, the central limit theorem for sample means.